yeah, and then I'm going to share screen for people on Teams. We'll share this window. Oh no, not that one. We want this one. Okay. You can see this, right, Grant? You can see that's the one I'm sharing. Okay, cool. Couldn't quite see screen full here. Okay. Yes, so welcome back, everyone. It is now day 3 of our stats and data science trainings of this week. And the topic for today is kind of to give you a very basic introduction to machine learning, what it is, how it works. We're going to do some extremely simple examples of it in R so that you'll get a bit of hands-on experience. And as usual, please, interrupt with questions, or if you get stuck on anything involving getting the code to run and so forth, I can help you, or my friendly assistant Grant is also here to help. And when it comes to the people on Teams, we don't really have a good way to do breakout rooms, so please just put something in the chat, and one of us will just help you in the channel. There's not too many people here, so I don't think it will be too disruptive. So yeah, please do not be shy if you need help. Okay, so I'm here on the course materials page for the week, and that's where you can find the full text version of the lesson with a lot more notes and details. And then the slides that I'm about to present off of are on here as well, in case you want to refer to them later. And for people who are not going to run the code on Scinet, if you want to run it on your own machine, here's the worksheet that's an R script with blanks left in it that you can fill in as you go. But if you're going to run it on Scinet, the worksheet's already on there, so you don't have to download that. And also, I have all my lessons have little homework problems at the end if you're interested, and there's answers on. If we have time, and we can go over them today. Possibly there'll be time for that. But before we get started with the hands-on part, I'm going to give a brief talk, an introduction to what machine learning is, how it might be useful to you as a researcher. On full screen. Okay, let's go. I think now I made these slides a couple years ago. I haven't edited them too much since then. I was just saying to Grant that it almost seems like quaint earlier time when, I didn't mention large language models and that kind of thing very much, which is basically another form of machine learning that obviously is of great interest to people today. But ultimately, all the stuff that we're going to talk about, how these models work, applies to large language models, and they work by the same basic principles as the simple models we're going to look at today. They're just somewhat more complicated versions of those. And yeah, the point today is to do some myth busting and cut through the hype, which, given the whole AI wave, is more hype than ever. So I think that's just as important as ever. Hopefully everyone here has at least some exposure to statistics, and because machine learning models are statistical models, so a little experience there will help you. And we're going to be using R, but we don't really have time to go through the fundamentals of how R works. So if you're already familiar with that, that will help you, especially R's syntax for writing the formulas for statistical models, which we're going to use, and the tidyverse packages for loading and manipulating the data, and for making some plots we're going to use, but not really explain that much since that's not the learning focus of today. Like all my lessons, we're going to be using an R script that has most of the code written for you, but a few blanks strategically inserted in the form of 3 periods, which you just delete those and replace that with the code, following along with what I do. But there's also on Signet, there's a cheat sheet version of the script that has all the blanks already filled in. So if you fall behind, you can just run the code off of that. Same way as it worked on Tuesday. Learning objectives for today, I've already mentioned a little, but I won't go through them now. But if you can refer to later, we're gonna just look at all these things, and then in terms of practical skills, obviously this will not make you an expert, but you'll at least have done this. If you make it through the next 3 hours, we're going to be taking a data set, looking at it, exploring it, and then doing any necessary processing to be able to fit a machine learning model to it. We're going to fit a couple different machine learning models. We're going to do cross-validation, which I'll explain what that is, and then show how we can kind of pick and choose among different machine learning models. With minimal modification to the code, we can fit a bunch of different models to the same data set, which can be useful. Okay, so here comes the conceptual background introduction to what is machine learning. We'll start with what isn't true, or what is sort of like myths about machine learning, and try to bust them one by one. So, you know, as a statistician, maybe I have a axe to grind here where, you know, statistics is considered this old, not as cool way of doing things, and now we don't, you know, do statistics anymore. We do machine learning, which is more like computer science and not mathematics or statistics. But you know, and statistics obviously has been around for, you know, in its current form for about 100 years. Its limitations are kind of well known, what it can and cannot do, but now there's this shiny new thing, machine learning, that people think can do anything. But really the difference between the two is not as big as it's made out to be, because machine learning models are fundamentally, they are statistical models. And like I said the other day, all models are wrong, but some are useful, right? So models are not reality. They are based on assumptions about reality, and also data that comes from reality. If the assumptions aren't true, or if the data is not good, the model's not going to be good, whether it's statistics or whatever, machine learning, whatever you want to call it. So yeah, this just shows machine learning, and also obviously AI is statistics dressed up with a fancy framing, in my opinion. There's also kind of an aura of mystique around machine learning, that it's like they're very complex models. It's a black box. We don't really know what they're doing, but they give us magically the right answer. You know, to some extent, yes, like some of these models are complex, and there's a lot of theory behind how they work that I'm going to kind of gloss over. But you know, in terms of actually implementing, it's not that hard. A lot of software tools are out there that make it easy, you know, especially now with vibe coding and everything. It's almost too easy to do without a good understanding. But I think, yeah, there's, you know, the barrier to entry of actually being able to do some machine learning is not that high. But I think, as with any tool that you use, you know, whether it's an instrument or I don't even know what, it's behooves you to have at least a modest level of understanding of how it works, even if you don't understand every single facet of it. And another thing that people often think is that you need big data to do machine learning. And here I said that big data is even more hype than machine learning, but honestly, that's, you know, so 5 years ago, because no one says big data. You never hear the term big data anymore, which you heard a lot 5 or 10 years ago, because now everything's big data, so no one bothers to say big data anymore. But you know, ARS researchers, some of us are producing big data, you know, in the genomic space, and people that generate a lot of images and that kind of thing. Those are truly big data sets. But even some of the small hand-collected data sets that ARS researchers work with can benefit from machine learning techniques to analyze them. So you don't have to have big data for this stuff necessarily. And another one is that, if you think, okay, I only work with small scale controlled designed experiments, so I don't really need to do machine learning. Well, I think that maybe you could get by with only classical statistics, but I think some of the techniques and concepts from machine learning, especially the focus on prediction, which we'll talk about more later, is changing the way all statistics is done and all research is done. So even if you don't become a practitioner and use these models a lot, having some basic literacy in it is incredibly important, because you're going to see it. You see it in our everyday lives now, but certainly in the literature, you're going to see some of this stuff, and it's good to just know what you're reading so you can understand it, what people are doing. Okay, so that's what it's not, but what is machine learning? The definition, the sort of most basic definition, is machine learning is any job you give a machine to do. By machine, understand computer, that it gets better at the more data it gets. So, that also applies to like statistics, right? A regression trying to use X to predict Y. A computer can do that, and the more data you give it, the better it will get. So even something like a linear regression can be classified as machine learning in that sense, because it makes predictions, right? So machine learning models, which is a type of statistical model, is a machine basically that takes data as input and spits out predictions. And ideally, the more data you get, the better predictions you'll get. If that's not the case, there's sort of a fundamental flaw with the model. So what are these jobs that a machine can do for us? There's kind of two main types that we're going to be covering one example of each today: regression and regression would be like the one on the left, where the outcome variable is continuous and we're trying to predict the continuous value. Classification would be predicting which of two or more discrete categories something belongs to. We're going to go through an example of both. And first one we're going to go through is classification. So there's sort of two main types of classification tasks that a machine learning model can do. One is called supervised and one is called unsupervised. Supervised is when we already know ahead of time what the categories are, and so we have some data where we know the categories and we have some other variables associated with that. And then what we want to do is then, if we get some new data where we know the variables but we don't know the category, to predict from those set options. Unsupervised is when you just have a bunch of data but there's no predefined categories that each data point could belong to. You don't know that beforehand, but you're just trying to find natural groups or clusters that are defined themselves. What's an example of each of those? Supervised would be like, for example, if you take a bunch of clinical measurements on patients, some of which have heart disease and some don't, then you fit a model to predict whether someone has heart disease. Then later you could take clinical measurements on a new patient and then say, what is the probability that that person has heart disease? And if we don't know it for sure yet, that would be supervised. Unsupervised would be, a lot of algorithms, unsupervised algorithms are out there. One example would be Google News. Google News pulls in text data, news articles, and there's no predefined categories they belong to, but it tries to figure out, okay, these two articles have a lot of words in common, so they're probably about the same event that happened in the news. So then they put it under like the same heading on the Google News site. So an unsupervised classification algorithm is being used to do that. And supervised learning, that's nice, but it does require better quality data. You actually have to have for supervised learning, you actually have to have a data set where you know what categories things belong to. Honestly, a lot of the stuff that we would be doing in ARS would be more the supervised type, but for really large scale things like, classifying news articles and stuff, that often requires that unsupervised approach. I'm sorry, I should say, if anybody has any questions or comments, please chime in whenever. ARS scientists do a lot of machine learning. That scientists that I collaborate with in the Southeast area, a lot of genomics breeders in ARS are using machine learning models to predict breeding values essentially for different organisms. And there we've got folks that are taking a lot of images and then classifying those images to see, where are weeds in a field, or try to classify quality of the crops based on the images and that kind of thing. We have a lot of people doing omics, like microbiome data in ARS, and we've got people that work on human nutrition in the Southeast area in Little Rock that are trying to look at does different diets of pregnant women affect the microbiome, their microbiome, and the microbiome of their offspring. And when you got omics data, you have kind of a lot of variables, like one for each species of microorganism, and so you can use machine learning techniques there as well. Those are just two examples. Okay, machine learning. Now back to kind of the big picture again. What the classification and regression that we just talked about are both types of prediction. Machine learning is all about prediction. There's sort of two, but prediction we want to distinguish from inference. Inference is what is kind of like what scientists do. We take a pattern in the data and use that to understand processes that are going on in the world. Like, why does something happen? Why does drop an apple and why does it fall, and things like that. That's making inference about the mechanism of why stuff happens. Prediction is we want to take a pattern in the data and then just correctly reproduce that pattern in a model. And so that's more like the how is more, we don't really care about why. It's not the goal is not scientific understanding necessarily with a machine learning model. The goal is just to predict, which in a way is easier. So machine learning people have it easy. They're not really necessarily doing science. They're just trying to get the right answer. Obviously, you need good prediction to make good inference, but prediction could be your end goal. But prediction is not necessarily always good. Prediction can be made even better if you do have that deeper understanding of why stuff is happening. And you can get a lot of good predictions just from correlational data, right? Without actually having a true causal association between variables. If they're highly correlated, you can make a good prediction. Like the classic example is, on days or like in times of year when shark attacks are higher, ice cream sales are also higher. And, that's because they both occur more in the summer or whatever. And so you could, but if you wanted to, right, if they're perfectly correlated, let's say, you could make a predictive model, go collect data on shark attacks, and use that to predict how many ice creams would be sold. It could work very well. You could get very accurate predictions, but so as long as that relationship holds, right? But that's not a true causal relationship. So if it's affected by the confounding variable of what season of the year it is. So like if something happened, like if sharks were extirpated from that area and then there were no more shark attacks, it wouldn't actually affect how much ice cream people would buy. So the relationship would break down and the model wouldn't give good predictions anymore, right? So ultimately, a model, even if it's just a prediction machine, is better if it truly incorporates those causal relationships of what's actually happening in the world. when we do fit machine learning models, we want to make the most accurate predictions possible. We want to make predictions that have the least amount of error as we can to be wrong as little of the time as possible. And I'm not going to show you a lot of equations and stuff like that, but this is the conceptual verbal description of how that works. We basically, a machine learning model includes and all statistical models actually give you what's called a loss function. That's a function that when we evaluate it, it tells us what our prediction error is, how wrong we're. Like in a regression, the residuals tell you the loss function, right? You want to minimize, like just if you're fitting y by x model, you want to minimize the sum of the squared residuals. That's what linear regression is doing. So that's the loss function for a linear regression, the sum of the squared errors or residuals. Machine learning model is no different. We also want to minimize the error and find the best fit. But you don't always have to use some of the squared residuals like you do in a classic regression. You can also use not only the mean squared error, but also the mean absolute error, which is basically just the sum of the residuals without squaring them. It's less sensitive to outliers, which can be a good or bad thing. And that's for regression where you're predicting a continuous variable. But if you're doing classification where you're predicting binary or discrete classes, there's different loss functions for that. A key difference, sort of like the key difference between machine learning models and classic statistical models is this idea of regularization. This is like really what makes machine learning as distinct from classical statistics. Although classical statistics does have some of this as well. Regularization is the idea of we don't want to underfit and we don't want to overfit. We want to fit a model that captures the signal in the data, but is not capturing noise, random variation, right? So if we here's the same data, but different models fit to it. The one on the left is just fitting a straight line through. It's kind of underfit because it doesn't capture that, part where it's sort of flat and then goes down, right? The one on the right is overfit. It's trying to capture every random squiggle in the data, which could just be noise. It has too many parameters. It's overfit. The one in the middle kind of strikes a balance. It probably has a medium number of parameters. It's actually capturing the patterns in the data that matter, but it's right in that sweet spot, right? It's fitting the signal, but not the noise. And regularization is basically a term for anything that makes a model less specific to the data set it's fit to and more general. That's what regularization is. That can include, like if you do a stat model, not machine learning, and do any kind of variable selection or model selection, that's regularization. If you have random effects in your models, that includes a component of regularization as well. But machine learning is all about regularization. It's a term that you'll see if you look at the machine learning literature. Like I said, regularization involves finding the sweet spot between overfitting and underfitting. You don't want to have training data is the data that are used to build the model. You don't want your model to fit perfectly the training data. You want to actually fit it a little bit less perfectly so that you have a more general model that makes better predictions on new data that wasn't used to build the model. And machine learning models, just like statistical models, have parameters like slopes and intercepts, but they also have what's called hyperparameters or tuning parameters. Those are additional parameters that you can sort of like turn the knob to set exactly how much regularization there will be to balance between overfitting and underfitting. And I'll explain how we find the best value for those tuning parameters as we go forward. How to fit a machine learning model. I guess the image didn't show up, but it was just a picture of a robot or something. way that usually machine learning models are fit. This is kind of different from how classical statistics is done. Like if you all would do an experiment and collect some data and fit a model to it, you would fit a model to the whole data. You wouldn't leave some back. You would probably fit a model to like the data from all the replicates that you collected. That's not typically the way that a machine learning model is fit. Usually you only fit a model to a subset of your data called the training data. Training is sort of the machine learning term for fitting the model. And then you save another portion of the data for testing the model. And so basically, so we have a training data set and a test data set. Ideally, they should be independent of each other. There shouldn't be random noise in the training set, should not be correlated with random noise in the test set. If it were, that's called data leakage, and that is a problem because it will give you overly optimistic assessment of how well your model is doing. If the model is fitting to random noise, and then you test the model on data that contains that same random noise, it will tell you your model is a good fit, but it won't actually fit well to new data that doesn't contain that same correlated random noise. So you want your training set to be independent from your test set within reason, right? Like if you, the idea, a model should be transferable. It should be able to make predictions in new contexts beyond what it was actually fit to. But that can only go so far, right? Like if we trained a machine learning model to take pictures of fields in Mississippi and identify the location of weeds, we would probably say, well, it can work in similar crops to what it was fit on. But if we like tried to, use it to look at weeds in wheat fields in North Dakota, it might not work very well because it's like very far out of the context of what the data set it was trained on, but it might do well in other southeastern states or something. So you want them to be independent, but within reason. So should be sort of, again, there's kind of a sweet spot there. You want to go independent, but not go too far, if that makes sense. The ideal would be if you had a training set and sort of a separate independent test set to validate your model on. Often we don't have that luxury. We just kind of have one data set. So this is what people do often in practice, is internally validate the model. If you can't externally validate it with an external data set, you have to just kind of split up the data that you have and set aside a portion of it and use that as the validation set. And so the model never sees that validation set. The values in it are not used to fit the model, only to test how good of predictions it's making. And it's like, well, that's a waste of data. Yes, but it's something that you have to do if you don't have the luxury of having a separate data set. So like, there's no rule for this, but like depending on the size of your data, you might take 10 to 20% and reserve it as a validation set. And this is where it's very important to minimize data leakage. If you have to make sure that, well, first of all, that the validation set is representative of your data. Like if you have 5 different cultivars, you're trying to predict what individuals are part of. You want both the training and the test set to contain a good number of examples from all the categories, but you also want to minimize or eliminate data leakage. And I'll explain a little bit more about how you might do that. But if if you're splitting up your data set like that, there's always the risk of having sort of non-independence between the training and test set. So that's just something to be aware of. Machine learning, no different than any statistical analysis or anytime you work with data. We shouldn't just jump straight into fitting some fancy model to the data. We should actually look at and explore our data and visualize it before we start throwing models at it. There's no difference between, that's not unique to machine learning. That's just a good practice in general. Obviously, some data points represent errors or are wrong, so we want to remove those. But they're sort of sometimes you don't want to clean your data too much in terms of getting rid of like outliers just because it's very high value or very low, because when it comes to actually making predictions, maybe those extremes really exist in the world, and you won't be able to clean those data since you won't know the true value, right, when you're really out there predicting. So you don't, you want to get rid of errors in the data, but not just throw out outliers just because they don't fit your preconceived notion of what the value should be. But there's no difference between that and classical statistics anyway. Right, so machine learning, because it was made by computer scientists and not statisticians, uses different terminology for stuff. Like we usually call, like in statistics, predictors or covariates or things like that. Well, in machine learning, they call them features. So that's what you might see in the literature. An X variable that you're trying to use to predict something is called a feature. And a good step when you're fitting a machine learning model before you actually fit the model is you can select which features you're going to actually use in the model. One good way to get rid of features that are just going to provide noise and not add any additional information is to remove features that don't have very much variation. Like if it's a binary variable and you have 1,000 rows and only 2 of them are ones and the rest is zeros, there's almost no variance in there. There's no variance in X, so you can't really explain variation in Y since there's no variation in X. So those are ones to remove. Also, if 2 of your features are almost perfectly correlated with one another, the second one is not giving you any more information. If you know one, you know the other. So all that's going to do if you include both of them in the model is to slow down the computation time it takes to fit the model without contributing anything to the performance of the model. So you can get rid, if you have 2 highly correlated features, just pick one and use. It doesn't matter which one, right? Because we're not caring about why things happen, right? We only want to have something that predicts. So it doesn't matter which one you get rid of. Another pre-processing step that's important. Some machine learning packages will do this automatically for you, but it's good to just do it manually sometimes so you know how to do it, is to standardize variables or transform them to a common scale. And often when we say standardize, we mean Z transform, divide, subtract the mean and divide by the standard deviation. That's a Z transformation. And then everything is in units of standard deviation with a mean of 0. If you don't, sometimes if this is not done, the model will give more weight to variables that just happen to have different units and are in a higher order of magnitude. Could be like you measured something in millimeters, so it's in the thousands versus, something that's in hectares and is only 2 or 3 or something like that. And a point to note is that if you do standardization, right, the mean and standard deviation are calculated off the data. You want to do that separately in the training set and the test set. Otherwise, information about the mean and standard deviation will be shared between the two, and that can cause leakage, right, where there's unwanted correlations between the training set and the test set. So you usually do it separately. Any questions so far? Great. Once we have pre-processed our data, let's actually fit the model, right? We want to fit a model, estimate parameters of the model using the training set that will give us the best predictions on the test set, on new data that the model hasn't seen before, right? So some of the parameters, just like slopes and intercepts, will tell us the relationship between the predictors and the outcome. And there's other, like I said a minute ago, special parameters, tuning parameters, like on a mixing board. They're special parameters that help us figure out the optimal amount of regularization to avoid both underfitting and overfitting and get us right in that sweet spot. How do we do that? One very common way of of determining the best tuning parameters is called cross-validation. You may have seen this before because it's also done in classical statistics sometimes. What cross-validation is when you repeatedly split a data set into training and test sets, fit the model on the training set, and predict the test set, and do that again for a different split until all the data points have been predicted once. So what you pick a value K, and often people use 5 or 10, and split the data set up into K equally sized chunks called folds. And then you basically, like if we're doing 5-fold cross-validation, first we take 4/5 of the data, fit the model to it, and predict the Y values for this other 1/5 of it. And then we repeat that, but use a different 20% of the data than before. We do it 5 times, and now we have predictions for every point in the data set one time. And you basically choose of some values for tuning parameters, do that process, get predictions, then take another value of the tuning parameters, do that whole cross-validation process again, keep doing it for every possible combination of tuning parameters that you want to test, and the one set that minimizes the loss function, that has the best prediction performance on the cross-validation test set, is the one that you're then select and say that's our optimal set of tuning parameters that minimizes overfitting and underfitting, and that's what we're going to use for our final model. That's how cross-validation works. It can be sort of hard to wrap your head around the first time you see it, though. So if you have need any clarification, please let me know. And then sometimes also, after doing these many cross-validations on every combination of tuning parameters, then you might do the whole thing again, but split up the folds in a different way, because you don't want your results to be reliant on some specific random split of the data into 5 chunks. You might want to redo that. So some people do, so you do 5-fold cross-validation for every combination of tuning parameters, then repeat that entire process, say 10 or even 100 times, using different random splits of the data into folds. But it's not always good to just completely randomly split up your data into folds. Like, for example, you have blocks, a blocking structure in your data, or spatial structure. You want to split up your cross-validation folds so that an entire block is only in one fold. A block is not split up across folds, because if you include data points from the same block or the same rep in multiple folds, you will get an overinflated estimate of model performance, because it will be capturing that random noise between the training and test set is going to be correlated, but not, and then it'll think that random noise is actually important for prediction. So if that makes sense, you want to, like if you had, we'll actually do an example of this later. Like if you had a experiment with 6 reps and wanted to fit a model to it, you could do like 6-fold cross-validation, and every time use the data from 5 to create the 6th one, and then repeat until all reps have been predicted. Now, once we have done all this long and tedious process of cross-validation, what I often recommend is like, okay, we firstly split the data into training and test set, then within the training set, do cross-validation, then take our test set that we've been keeping under lock and key the whole time, not letting the model see it. Now we fit our final model to the entire training set and then use it to predict the test set. This is like the moment of truth, where we really see if our model that we've extensively internally validated also is externally valid and does good on a completely new data set. Yes?
So if we have 6 replicas, 4 of them is a tuning, 1 is a cross-validation, like you said.
Yeah, you could keep an entire rep and not include it in the cross-validation and only use it for final testing. Yes, that would be a good way to do it. And did we make a good model or not? that depends on how good of prediction performance we get on the test set. You know, there's no like one rule of like what is significant or what is good enough, because prediction is a practical goal. So like, is it good enough? You know, are you okay with being 5% off, or is that not good enough and we have to be within 1% of the true value? You know, it really just depends on your stakeholders' needs or your needs, right? Like that's what matters in terms of how good the prediction performance is. So it's really up to you if the model is good enough, or if you have to either go back and try to fit a different model, or say there's just no signal in this data that will ever get us to a good enough prediction that we need, so we have to go get more data. It's a practical, and this is just a graphical illustration of what I just mentioned, right? First, we have our data set, split off a testing set that we're never gonna let the model see during the model building part. Then we train our model using cross-validation to identify the best tuning parameters. Then using those optimal tuning parameters, fit the tuned model to the entire training set using the tuning parameters that we identified in cross-validation, and then turn that model loose on the test set, see what predictions it makes, and see how good we did. That's sort of a model tuning pipeline that is very common to follow. I mentioned that machine learning models are mostly for prediction, but it is also possible to do inference and actually look at what variables are driving the predictions that we make using machine learning models. And there's sort of, because machine learning models are often not just strict linear regression where you get like one slope parameter for each predictor, they often are nonlinear. And so it's very hard to directly interpret the parameters of a machine learning model as having some biological meaning. There are a bunch of methods that are used to kind of like extract out of those many parameters an overall score of variable importance for each variable, which then we can use that to make inference of like, okay, you know, this particular you know, trait or genetic attribute is like very important for determining our outcome of interest. We'll mention that a little later. Yes, Grant.
And what would you recommend to be a good size for a training population of a prediction model?
I mean, it's very, very variable depending on the model. But in terms of like relative size, usually like I would say, if you have a big data set, you could set aside 10% for the validation set and keep 90% to fit the model too. Sometimes you might need to do, paradoxically, if you have a smaller data set, you might need to set aside a bigger portion for validation because you want your validation set to be big enough to be representative of the full data set. And that's maybe not possible in a smallish data set if you only have 10%. So yeah, it just depends. In terms of how many observations you need, there's no real rule for that. I mean, you know, like a lot of machine learning models are fit to, you know, whether it's ag science or clinical trials, you know, the sample size is not huge, right? Like clinical trials only have like a few dozen people in them. And obviously our ag studies may only have a small sample size, and like, that's still fine. You know, you can fit a model with only tens, dozens of sample size. It can still work. It just depends, you know, the more the better, but you know, a small number is very common.
I guess as a follow-up, are there any methods you can use to tell if your training or testing sets are representative, like either of each other or like of a larger population?
That's a good question. Are you thinking of something, or this is not a rhetorical question? Yeah, I don't know, like formally what you would use. I mean, obviously, like there are kind of like ways to set up stratified random sampling to make sure that that you select a representative sample from. Right, like I mean, if you have a large enough data set, right, randomization will take care of that, because if you have a very, very, very big population and take a big enough random sample, it converges on what the central limit theorem tells us. It will converge on the properties of that population. But yeah, I don't know what, that's a good question. There's probably like some diagnostics you could do or something, but I don't know off the top of my head. Good question though. I mentioned that there are a lot of different kinds of machine learning models out there. And again, so our goal is prediction, right? So we don't necessarily care which particular algorithm, which model we use, as long as it gives us the best performance. We're allowed to, it's not cheating to just go pick 10 different machine learning models, fit them all to the data and say, hey, this one performed the best, so we're just going to go with it, right? Because as long as you use regularization to prevent overfitting, it's a fair comparison, and you can just pick the one that performs best. More complicated is not always better. Sometimes simple models that are basically just regression models do better than very complicated nonlinear models. And I think, I mean, as scientists, yes, prediction is important, but we do want to also have some understanding. So I think, to me, the best model is one that gives you good enough prediction performance, but that you can actually understand a little bit of why you got the result that you did. Since again, we are scientists, and understanding is our goal too. And if you liked that workflow and thought it was cool, then how come you were not taught to do this? Cross-validation could be done without a machine learning model. It could just be done with classical statistical models, regression models. You can cross-validate. Like, why don't people always fit model to all our data? Why don't we use cross-validation? Well, honestly, it would be great if more people would do this workflow in conventional statistics. And we don't want to overfit in classical statistics either, right? It's not as bad of a problem if our goal is understanding and not prediction, but it's still a problem, right? We don't want to fit our model on random noise, because that's not going to increase our understanding of the world either. I mean, if you look at the scientific literature, you can't go far without running into publications that are kind of based on data mining and pulling correlations out of data that could be random noise, and there's no way of knowing, right? So, I think this focus on prediction performance has trickled back to the world of statistics, and more people are starting to do this. And it's, the stricter of a test you can make a model pass and still give good predictions, the better, both for prediction and for inference, for understanding. I'm almost done with the intro part, then we'll take a quick break before we get to the hands-on part, but just a couple more slides here. Software-wise, machine learning models are implemented in a lot of different software platforms. We're going to use R today. There's sort of computer scientists and people that do machine learning like Python a lot. It's sort of thought that Python is better for machine learning, but honestly, it's very similar to R in terms of the capabilities, and also SAS does a lot of machine learning models too. So if you're an old SAS head, you still can join in the machine learning fun. A word of caution before we continue, and I wrote this before, like, vibe coding with AI models became a thing. It's even more true now that, they're sort of like, people don't want to be gatekeepers and say you have to know a lot of coding knowledge to be able to fit machine learning models. You want to make it easy and accessible to everyone, which is great. Like, let's put our data in and get a result out without knowing what went on behind the scenes to get that result. That's good, and it can be very useful in many cases, but I think the ability to understand how the model works can help you refine the model to your particular situation best. So it's good to have at least some understanding. And that's part of a lot of machine learning R tutorials you'll see will use a package called tidy models, which the goal there is to really minimize the amount of code that you have to write, and it does everything on the back end, and you just sort of do very simple code on the front end. But I'm not using it in this tutorial intentionally, because I think it's good to make things a little more explicit. Later, you can go and look at tidy models if you want to do machine learning in R, once you have a little understanding. big picture, bringing it all together, I mentioned we want to, in machine learning, there's these things called tuning parameters and regularization penalties that say we want to not overfit too much to our data set, make our models more general, and make better predictions. Well, mixed models use random effects to not overfit too much to your data set and make more general predictions. The Bayesian approach uses priors to not overfit to your data set and make better general predictions. It's all the same, right? Those are all different tools to sort of get the same outcome. The more tools we assign to know how to use, the better, but they're all conceptually trying to achieve a similar goal. That concludes the intro. Let me take any questions that folks have for a few minutes. Does anyone have any questions so far? So yes, maybe you'll have more questions when this is not so abstract and we actually see some of this in practice. So let me let's see, maybe we can, let's just go ahead and take a 15-minute break until 10 after, and we'll both take a break. And then anybody who hasn't got their SciNet environment set up yet, we can do that in the next 15 minutes. So if anyone on Teams needs help with that, we can do that now. But I'll yeah, otherwise let's come back at 10:10 for the hands-on part. So let's see. I will. Yeah, so Amar, you need to set up your SciNet thing, right? So if anyone, yeah, I'm gonna leave the podium here, but I think we're still monitoring the chat, so we can, if people in Teams need help, just put in the chat. So yeah, let's just go ahead and get you set up. Hard. Okay, oh, you're already on that. Great. So now click connect to our SQL server. Excellent. See, you're already halfway there. Yeah.
I do. Black box is so sensitive. Next to you come out of the
Yeah, I always had to just put Siri. Okay. Yeah, so that's from last time. Okay, so now. Yeah, so the last time you used this was from last summer.
Yes.
Okay, so now, do you have the like course page open that has the link to the it's fine, it's not the text like what you need to. Okay. So the only thing you're gonna have to do is install Stoneville. So you plug the window, but if you open it again, it'll still be there.
It's in there, but it'll come out.
Chocolate. Oh, yeah. Or you can check. Yeah,
Okay.
thanks. You can go back to the video server thing. Just go, not the big one, but that one, yeah. You could have. Yeah, that, and there should be one running now. Yeah. Yeah, just go back. Yeah. Now go, when you go to the chat, just go Grant, just pasted the two. Yeah, just copy this right here, those two lines. Yeah, copy that. And now go back to our studio server, click on the terminal. And then just right click, don't hit Control V, just right click with your mouse and paste. That will bring it out to ours. We're good. We see the phone, but yeah, just click on it. It's like Control V, we'll copy those, we'll enter. Each thing double click in there. Good, and now we have to open the project.
Yeah. Right here.
And we're going to type in the path of the project. So you're going to type /90 data /shared /
your username. I'm in.
Oh, that's okay. Okay. I saw you.
Yeah, okay. Oh. Now you can open this.
Is that one?
And be in the dark.
Oh, Joyce is there.
And that's. So just click on that. Yes. And now you're all set up. So then you can open this worksheet. Okay. You can open the machine learning worksheet there. Yeah, that was from Tuesday. Now we're gonna do, not that one. Yeah. That's it. You're all set. That's what we're gonna be working off of for today. Yeah. Yeah. I have.
Okay.
Okay, cool. But yeah, it's also there.
Is that it?
Yeah, well, you can run it on your own. You don't have to use Skynet. You could run everything on your own. If all the packages are installed, you could. It's up to you. But now you have both options.
Yeah.
Yeah. Yeah. Yeah, that's from, and then that's the only one, that's our analysis one. So that's not what we're doing today. We're doing the machine learning one.
Oh.
And I was like, there are a few data, example files, but there's one on each one from a folder, and one from HRL. But you'll scan it. You know, yeah, so down here, this one here. Oh, yeah, it's one. Once that's done. There we go. We have a next thing. Yeah, I put the wrong way on. I put the wrong one. Go, do that. No, that's the right one.
Yeah.
Yeah. That's, same one.
Yeah, that was great.
Yeah, I did.
I started there.
Oh, yeah, yeah.
Started one down. Oh, I see.
Yeah.
Yeah,
That's a debt.
I have been running this.
Yeah, so now you could run everything on Skynet or on your own, or it doesn't matter which one. Yes.
It's a run.
So you run every one. Okay, so you're just gonna do it on your own.
Perhaps, and also, like this one, supposed to be the,
Just takes a minute or two.
that's the assembly.
Yes. Yeah. What we're talking about. So. No, I mean.
Okay. It's a Chingo.
So, you know, but I don't.
There's also,
Yeah, doesn't.
it's a summer, in the pack, like you said, yeah. Summer.
Yeah. That.
Yeah.
It's good for that. We're gonna put the next folder. The 90-day data flash here. Are you on the sign out? Are you sign it? Yes, you're all good. So now you just go to file, just a temporary folder there. These files, you open that machine learning worksheet. We see all the small. Yep, you're all set. I'm getting on. Yeah, and there it is. So then. Or. And then. There you go. And then now you can try to become the working. So we try this.
So,
And then we're on the-
How you doing?
Hi, how are you?
All right.
Like in statistics, we can do like a clustering and
Yep.
classification.
Yep.
So
That's what we're about to do here. Yeah.
are they using the same tools we use in statistics?
Yes. Yes. Basically, yes. I mean, it's you know,
Like PCA,
yeah,
PCA.
You're right. PCA was invented in 1904 or something. It's been around for a very, before anybody heard of machine learning, PCA existed, and it's, yeah, it's doing something very similar than a lot of the machine learning models are doing. Just that the machine learning models perform better than PCA on large data sets, but on a small data set, PCA is just as good as any machine learning model.
Yeah.
Your networks are systems being used for.
Yeah, neural network is a type of machine learning model, like all those large language models are neural networks.
That's from the
And
biggest jump.
they're complicated, but they basically work with the same idea of any of this stuff. They have a loss function, they use regularization, they do all the stuff we just talked about. They're just
And then the way.
have a lot more parameters than a statistical model would have. But yeah,
The dots are what
So
you.
when you talk about the cross validation,
Yep.
like a one, you shoot it like a 1 to 5,
Yep.
your 1 to 5 are from the training data set.
You'll see.
That's right.
Okay.
First, we split the training and test, then within the training set, we split it up.
Yes.
into
Oh,
four.
okay.
Yeah, that's what most people do. Yeah.
Slides here, you can see date, and there's much for CSV, that's the line run. And then.
Use 3 replicates, but statistically, how many replicates is there?
It depends on how much noise in the data, you know? Yeah, it really
Yeah,
depends.
yeah, we'll do it.
Yeah, I was just asking.
Yeah.
Like, usually
Yeah.
go like 3 to
Okay.
5.
Yep.
Per genotype,
That's
per
usually what I
think-
treatment.
Yeah. Part of it is here, we're constraints on what you can afford to do and what you have time to do, and part of it is, and then we're state determined by how much statistical power you want to have, and
So maximum.
that also applies to machine learning. I mean, eventually, you will reach a limit where adding more is not gonna help your performance, but
But minimum
nice
is
to-
3.
I mean, yeah, I think 3 is kind of like the bare minimum, you know, it's,
You can go.
because
higher.
like, yes, you can always go higher, right? Because if you're trying to look at, you know, like, let's say you want to estimate a normal distribution, right? Well, normal distribution looks like this, right? It has a mean and a standard deviation. Well, you know, this, to define this nice smooth thing, you're gonna need more than 3, like, if this is like 3 data points, you know, or if you have like, you have a histogram with only 3, right? It could look like this. That doesn't look like a bell curve, right? But like, let's say you had, 10, it might look like this, and now we're getting closer. So it's, to know the mean, you only need a few, but to actually know the variation, you need more. It just, the more you get in, once you have like,
What you're
once you
seeing.
have 100, it's gonna look like this. Getting closer to that, yeah, I think 3 is enough for some, but for some things, 3 is not enough. It depends on how much noise there is. Yeah.
There you go.
Okay.
All right. Well,
Good.
Yeah, have you used that video before?
when you talk about dividing the data, you mentioned
No, you know how to find
our
out.
application from blocks go by
You
blocks.
just flip
That's
it
right.
on.
Yeah.
If you have multiple years of data, you still do the same.
You could also, yes, if you had like
All right.
2 years or 3 years of data for 10.
data,
Yeah.
like you could model to 2 years, maybe to the third year.
Yeah.
Yeah. Year is also like data from the same year or not independent. So it's like a structure. If your data has any type of space or time structure, you should take that into account. Of training and testing. Yeah.
If you have only 2 years, you can still do the same, like.
Yeah, I mean, and then you have like a 50-50 split. Yeah, you could still do that. Because yeah, I mean, that's what you're going to be doing in reality, right? Like you have, if you fit a model the data from 2023, 4, and 5, we want to predict what things are going to be like in 2026. We don't yet know the exact weather that's going to be on every day in 2026, right? So you can kind of simulate how it will do by eliminating 1 year from your data set for testing and then see how it does. And if it does good on that, you can say it'll probably do good on a new year that has never existed yet, right? Yeah. So we'll get started again in just a minute here. Let's see. So I will, in just a minute, resume and give an intro to the example data set we're going to be going through. Then I'll get into open up our studio server on Sinet, and then we'll actually start running through the code together. So we're going to do two demos for the rest of the time we have here. We're going to do two demos. The first, we're going to do a classification task and a regression task. Like we said, those are the two main type of prediction tasks that machine learning models can do. And what we're going to do is use attributes of measurements taken off of photographs of different dates, fruits from a date palm tree, to see if we can classify what cultivar they belong to based on those measurements. The place where I got this data set from is kaggle.com. It's a pretty interesting website where they basically do like machine learning competitions. They'll put a data set up there and then say, basically give prize money to whoever can produce the best predictive model to predict something from that data set. But it also just has a bunch of example data sets, including a lot of ag themed ones. So it's kind of an interesting website. This one is, like I said, about 900 photographs were taken of individual fruit dates that belong to 7 different varieties. And then some sort of image analysis software was used from each photo, 34 different measurements, like the maximum diameter, the circumference, how wrinkly it was, and things like that for each photograph. So the data has basically 34 columns and about 900 rows. Each row is one fruit. So there's 34 numerical measurements, and then there's one column called class, which indicates which of the 7. So we already know what cultivar each of the date fruit that photos were taken belong to. What are we going to do? We're going to import the data set into R, explore it a little bit, clean it up, do our training, testing, split. Within the training set, we're going to do cross-validation, fitting a type of machine learning model called random forest, which I will take a little break and give a bit more background on exactly how that one works, and use our cross-validation to identify the best tuning parameter for the random forest model, then go back, fit that model to the full training set, and validate how well we did on the testing set. Exactly what we just talked about. We're actually going to do it. So I'm going to go in and I'm already logged into Series on Demand on Scinet. So if you're running your stuff on Scinet and haven't done this yet, you should do that. So yeah, if you go to the course page, there's under the run code on Scinet, there's a link to series-ondemand.scinet.usda.gov is the site you should go to. Once you go there and log in, you'll see this. Interactive apps. Go down and the drop-down menu and click on RStudio Server. I think most people have already done this, but and then we're going to start a job, request some computing resources from the server that I'm going to be using for a little bit to run code on. Under this stats training account, series, 400 thread, I'm not sure what that means. We're going to use R4.4.1, 4 hours, 2 cores, 4 gigs of RAM is plenty for the small things that we're doing. And then if you have -- reservation equals MS 2026, I have requested that Scinet reserve some of the processors for us to use for today, and that will just mean we don't have to wait in line for our job to start. Once you've got all that typed in, press the blue launch button. Is everyone good there? Or okay, cool. Hit launch. After a couple of seconds, this should turn into a button that says connect to RStudio Server. You will be able to use RStudio. You can do this at any time. Just get rid of the reservation equals MS 2026 because that's only for this week. But if you notice that we copied all the example data to a folder called 90-day data, that is only for temporary files, and everything in it, if it hasn't been used for 90 days, gets deleted. So if you I mean, you don't really need anything that's in there because all those worksheets are on the website and stuff anyway. But if you took any notes, you'll want to either like copy that if you and save it in 90-day data. You'll have to either export it and download it to your own machine or copy it to your home directory. It doesn't get deleted after 90 days. In a second, I'll show you how you can do that if you want. So I'll connect to RStudio Server. And okay, yes. So like, for example, if I, let's say I took some notes in this worksheet and wanted to export it, you can just select it and then go to more and export, and it will, then you can save it to your local hard drive. Yes, so here we are inside of RStudio Server. Is this a big enough, can people in the back see the code on the screen? Is that good? Y'all in the back? Okay. I tried to blow it up a little. Here's the worksheet. Oh yeah, if you're not already in the, I think everybody should be set up with the project so that you can see we're in 90-day data, shared, your username, and then you can open up the MS 2026 folder. Inside of that is a folder called Worksheets. You open that up. Inside of that is Machine Learning Demystified Worksheet. Click on that to open it. And here's the worksheet. Has everyone got there, either on their local machine or on Scinet? Okay, excellent. So the first thing we're going to do is load the packages. So you can highlight the block of code that contains all the library calls and hit Control-Enter or click Run in the top. And it'll give you some various messages, but as long as nothing says error, you're good. And then we're going to import the data. So that's the first thing we're going to do. We're going to import it to a data frame called date fruit using the read CSV function. And if you're on Sinet, you don't have to read it from this URL. You can just read it from the folder called data. And then the first thing we're going to do, and then in the same step, we're going to load it, and then we're going to convert the class column to a factor, which is a special R data type for a variable that can only contain specific category levels. Like this is an example of that. So class equals first, replace the first set of dots with factor and the second one with class. And as you can see, the C is capitalized because R is case sensitive. The variable name in the data has a capital C. So this one has to have a capital C. And you can hit escape to make this automatic autocomplete stuff go away. And then while my cursor there is on the line 25, I'll hit Control Enter. And here you can see it's displayed that there's 898 rows, 35 columns. One of the columns is text, class. The rest are double, which is means numbers with decimal points in them, basically. Okay. Everyone good? Yes, if you're on your local computer, there's no folder called data. You'll just read it in from where I've posted this CSV file on a website. So if you are doing it on your own machine, you'll put that factor class here instead. Let me see if I have anything in the slides. Yeah, so we're going to what we're going to do first is we're going to just explore the data a little bit. So I'm skipping this part because we don't need to import it from the web. It's already here on the server. We're just going to do some various things to explore the data. First function we're going to use is dim. That tells us the dimensions. Dim, short for dimensions of the data frame. You can hit escape to get rid of the auto completion. Hit Control Enter. It tells us 898 rows and 35 columns, which we already knew, but that's just another way to show it. Now let's take a look at how many of the fruits belong to each variety in our data. On line 31, I'll replace these dots with the table function. I hit escape. The date fruit $ class, that means pull out the column called class from the data frame and then make a table of it, see how many of each category there are. I'm going to hit Control Enter there. Oops. Not just enter. CLS. Okay, we've got a table there. Those are the names of the different cultivars and how many there are of each in the data. So this is kind of intentionally very nice data set that's very well balanced. We have every variety has at least 65 fruit from each variety. So if you only had 2 or 3 from a variety, you probably wouldn't be able to build a very good model because you wouldn't be able to put enough in the training and test set. So we have plenty so that we will be able to split up the training and test set and still have a decent number from every category. We need to have some of all the categories in the training set so we can build the model and in the test set so we can make sure it did well on those. But we have plenty for that. Now, the next line of code, I didn't leave any blanks for you. This basically pulls out the column names of the data frame, except for the class column. And those are going to be our predictor variables that we could potentially use to predict the class, the variety. So hit Control Enter to run that line. And now we can see in our environment, there's a vector of 34 names, which are the names of the different columns: area, perimeter, the length of the major axis, and things like that. Here it is. Okay. And This next line, we're going to reshape the data into long form, which is instead of having 800 and some rows and 35 columns, we're going to make it a really, really long 3-column data frame that has a column for the variety, a column for which numerical variable it is, and a column for the value. And that works better for the plotting function we're about to do to explore the data. So on line 35, change the first dot to pivot underscore longer. That's a function that turns wide data into long skinny data with few columns and many rows. The columns that we want to turn to long form are the predictor variables. So we'll replace this with all of parentheses predictor underscore variable. I can hit tab to complete that automatically if I start typing it. And we're going to call the column with the new variable name in it variable. That's what names2 equals variable means. Again, this is sort of tidyverse code, which is not the learning objective of today to learn how to use that. You'll just have to take my word for it that we're making long form data here. Control Enter on that to run that and create a data called date long. You can see in your data tab up there, it has 30,000 rows and 3 columns. Like I said, and then execute the next, put your cursor in somewhere in line 37 and hit Control Enter to generate box plots colored by cultivar for every single one of the measurements. And I'll zoom in on that. Hopefully that shows up on the screen share. You have, these are the 30 and some different variables that are measured on every single one of the dates, and the different boxes for the different varieties. So you can see, I don't really know what some of these mean, but it's like, okay, well, if we look at area, some of the varieties have larger fruit than others. You can see there's like a pretty good separation where some of the, there's not that much variation within cultivar. Some are just overall smaller and some are bigger and things like that. I think there's some things that show how wrinkly they are, and some are wrinkly and some are smooth and things like that. Yes, like I think there's like rugosity, I think is one of them somewhere, maybe. Some of these stand for how wrinkly it is. Yes, and so let me see. Oh, here's one that I just want to highlight. One that stands out is aspect ratio, the ratio of essentially the length of the width of the thing. They're mostly around 1, but one value is about 500 in the data set, right? So that's like, okay, that's probably a mistake. I don't think there's any dates that are 500 times longer than they are wide. So it's probably a mistake. And we can say, that's not just an extreme value, that's just an erroneous value. Let's get rid of it. And that's what our next, I'll close this plot. That's what our next line of code is going to do. Filter means we're just going to say that because that, even though only that one measurement maybe was bad, we're just going to get rid of that entire observation out of the data set because we don't really trust it anymore. So I'm just going to get rid, it's only 1 out of 900. So we're just going to go ahead and get rid of it. Filter means select only rows that meet a certain condition and get rid of the rest. So we're going to, on line 46, the column was called aspect underscore ratio in all capitals. So we're going to say aspect underscore ratio less than 500. That'll get rid of that observation. Control Enter. So right now, you can already see in the data environment tab that it only has 897 rows anymore, not 898. So we got rid of 1. But you can also use the n row or the dim function to check that. And so I'll hit Control Enter. 897. We got rid of 1 observation. If you went back and ran this ggplot again, you'd see that it was gone. Next thing, this is still all pre-processing. We haven't actually done any model fitting yet. Next thing we're going to do is, this is since we have multivariate data, let's look at whether any of the predictors, the possible features we might use to fit the model, are highly correlated with one another. I'm sorry, if people need help, I can pause for a second. If anyone on Teams needs help, please let me know in the chat. This is trying, the conference room computer that I'm on is trying to update Windows. I really hope it doesn't automatically reboot the thing while I'm trying to do this. If so, please bear with me. Yeah. So far, so good. The next thing we're going to do is look, like I said, if any of the variables are highly correlated with one another of the different measurements. If so, yes, we could throw them all into the machine learning model and it would probably deal with that, but it can be a good practice to do that step ahead of time, because with very big data sets, having a lot of highly correlated predictors that we throw in can make it take longer to fit the model without any benefit. So let's just go ahead, and it's just good for exploration anyway. So we're going to make a correlation matrix. Pairwise, all pairs of variables, we're going to calculate the correlation coefficient between them and make a matrix of those, and then make a plot of it. First, on line 50, COR, the core function, hit escape there. That is a function that produces a correlation matrix in R. And this next part of the line is telling it to only use the numerical variables in that correlation matrix, the predictor variables. Control Enter. And then we're going to use a package called ggcoreplot, which makes some nice, it's basically a pre-made function to turn a correlation matrix into a heat map. So on line 52, we're going to use the function ggcorrplot, ggcoreplot, which will plot our correlation matrix as a figure. The first argument is the correlation matrix we just made. The second argument is type equals lower, which will make, since the correlation matrix is symmetric, we're only going to show one triangle, one half of it. Hit Control Enter. Again, if you, yes, so there's a warning message there, but we can ignore that. Here's the heat map. Let's take a closer look at that. You can see that as the color approaches solid red, we have a perfect positive correlation between two variables, and solid blue means negative. Some of the variables are very close to having a one-to-one perfect correlation between them. So probably if we got rid of one of those, getting rid of it isn't going to lose any information from the data set if two things are perfectly correlated. Like for example, the area and the perimeter are highly correlated, obviously, and entropy RG is correlated with entropy RR. Those are basically two different measurements of how wrinkly the perimeter is. Those are correlated, things like that. So, and also if two things were perfectly negatively correlated, that would also mean we could get rid of one of them and be fine. So let's go ahead and get rid of some correlated variables. I'm going to use a function called find correlation, which is in the R package called caret. That's one, it's sort of a machine learning package that has a lot of functions that are just like make it convenient for you to pre-process data for machine learning models. And we're going to use that, that package quite a bit today. This is the first function we're using from it. So in line 54, we're going to use this find correlation, find, and then capital C for correlation. You can see once we start typing it, it pops up if the package is loaded, and I can hit tab to finish. We're going to, within find correlation, within this date correlation matrix, we're going to find any variables, any pairs of variables that are correlated with a correlation coefficient. And I decided let's use 0.95 as our cutoff. If two variables have a correlation coefficient of 0.95 or greater, we can get rid of one of them without affecting our model performance. Having both is not going to add any more information. And then names equals true means give me a vector of the, and this function doesn't give us every pair. It gives us like one of each pair of correlated variables. It kind of chooses it randomly, which one it gets rid of and which one it keeps. Hit Control Enter. Whoops. Yeah, not just enter, but Control Enter. And here's correlate. You can see in the data up here that it decided that we could get rid of 16 of the 34 variables without affecting, and that will make the highest correlation in the among any pairs that are left to be less than 0.95. Now I'm going to just go ahead and remove those columns from the data that we're going to use to fit the model. So now those 16 variables that we decided were highly correlated are not going to be in the model moving forward. How do we do that? On this line, we say we're going to use a pipe to say start with date fruit, and then we're going to select, which means choose some columns and keep only those columns. The minus sign means get rid of columns, and then all of, and in those parentheses, the last line of code, I created an object called correlated underscore variables, which is the names of the columns we want to get rid of. So we're going to get rid of those here. Correlated underscore variables. I can hit tab to complete that once I've started typing it. Now you see that date fruit has 35 columns right now. If I hit Control Enter and run this, execute this line, it now has 19 columns because we got rid of 16 correlated variables. All good? Now that we have done a bit of pre-processing, we are going to split the model into a training set and a testing set. Like I've talked about, we're going to pick, in this example, we're going to take 90% of the data and use it to build the model, and then we're saving 10%. We're not going to look at it for estimating the parameters. We're just going to use it at the very end to see how good our model is. Because this is a random split, if you want to get the exact same result as me, you will have to set the random number generation seed to the same value as me. I just put 1 in here so that you'll get the same result as I do. And another function that's very convenient from the caret package for training and testing split is called create data partition. And that is what we're going to use. So it's called create. Capital D, caret uses the camel case. So capital data, capital partition. You can see that comes up. So I can hit tab to complete. And this is going to use stratified random sampling to make sure that the training set and the test set contain roughly equal proportions of all the categories, the cultivars. We want to have good representation of each in the training set and the test set. So what column are we going to partition off of? It's going to be the class column, again with a capital C. And P, with what proportion of the data is going to be used in the training set? We want P equals 0.9. 90% of the data is training set. The rest is for testing. I forget what list equals false does. but the format that we need to output in is not a list. It's going to be, so I'll hit Control Enter to run that. Yeah, train index. Yeah, instead of a list, it's just going to produce a 811 integers. Those are the 811 rows in the data that are going to be used for training. And the rest are going to be tests. So that's 811 is about 90% of our data. Now we're going to create a training set, which keeps only those rows, and a testing set, all the other rows. So we want date underscore train as data frame. We want just a regular R data frame, not a tidyverse data frame. And these brackets say which rows and columns do we want to keep. And so we replace these dots with train index. So that's capital I index. That means training set, we want the rows with the row numbers that we selected from train index. And then date underscore test. It's the same, except see there's a minus sign there. So minus train index. Other than that, it's the same. So that means get rid of those rows and keep only the others. So date train and date test. And then I'll, yes, so then I'll highlight both those rows and hit Control Enter to execute. You can see date train has 811 rows, same columns. Date test is the other 86 rows. All good? And so now everything is good to go. We've cleaned up the data a bit. We've split into training and test. Now it's time to do cross-validation to identify the optimal tuning parameters for our random forest model. But what is a random forest model? Let me go ahead and go back to the slides for a minute and give a little background on what that is so that it's not a complete black box for you and you understand what the model is doing. So we did all of that already. Okay, what is a random forest? It's called random forest because it fits a bunch of decision trees to the data. So it grows a forest of decision trees. It's called random because every time, instead of fitting to the whole data set, it takes a random sample with replacement, like a bootstrap sample from the data set and fits a decision tree to that sample. But what is a decision tree? You may not have seen that before. It's actually a very simple concept. It's basically sequentially splitting up a data set with a series of rules that ultimately give you the class or value. Like this is a very simplified decision tree for, like, if we find an animal and want to identify what kind of animal it is, first we say, okay, I've got an animal here in my hand. Does it have more than 4 legs or does it have 4 or less? Okay, let's say it has more than 4. Well, does it have more than 6 or less? Okay, it's got more than 6. It's a spider. If it didn't have more than 6, it's an ant. So that's like the a very simplified. That's all a decision tree is. And this would be just like the exact thing we would do for this date frame, the date data frame. We say, okay, here's our date. Is it longer than 2 centimeters? If so, go to the left. Is it very wrinkly? If so, go to the right. And then it tells us what kind of date it is. That's exactly what we're going to be doing. Like I said, random forest. If you just fit one decision tree to a data, it can overfit. So what random forest does is it, like I said, fits a bunch of decision trees to different random subsets of the data, and then combines the predictions from all of those decision trees using a majority vote to give us a final decision on the classification. So if you take a random sample with replacement of a data set, not every data point, like if I had 10 data points and pick a sample of size 10 from that data, but I'm allowed to pick the same one twice, some data points are going to be picked more than once and some will never be picked. So the ones that are picked at any given time are called in the bag, and ones that are not are called out of the bag. I'm not sure why they call it that, but that's the term that's used. And basically, it is basing the final model, final decision tree on the prediction performance for data points that were out of the bag, that were not in the random sample. Now that already gives us some regularization. It already prevents from overfitting even internally. Random forest has its own way of regularizing and avoiding overfitting, but we're going to, even if you didn't do cross-validation, it would already have regularization, but we're going to be extra conservative and kind of double up. And on top of that internal regularization it's doing, we're going to also use cross-validation on it as well. I'll explain how that will work in a second. The carrot package is what we're going to use to build our machine learning models today. And the main function that is used in the carrot package is called train. That is a function that is used to train or estimate the parameters of a machine learning model. But before we run train, we're going to set the specifications for what kind of validation we're going to do on the model. And we're going to use cross validation with five folds. We're going to split a 4/5 and 1/5 split of the data, repeating 5 times until it's predicted all the data points once. So that's why method equals CV for cross validation and number equals 5. So we will use train, capital C for control. So this will just create an object that's a list of specifications for our model training procedure. Method equals, in quotes, CVs, and for validation, number equals 5. Some people use 10 for cross-validation. I think, 5 to 10 has been shown to be a good sweet spot in terms of the number of cross-validation folds you use. Now we're going to run that line of code, line 69, hit Control Enter. Set the random seed to 145. And then here, as you can see, this entire thing from line 73 to line 83 is all just one function call, calling the function train. I just split up the arguments on individual lines so it's easier to see them all, but basically train is just this one huge function that you throw a lot of arguments into, and then it does everything that you need to do to fit the machine learning model. It's going to do all the cross validation and everything. First thing we want is the model formula. Which variable in our data are we trying to predict, and which ones are we using to predict it? So form means model formula. That argument, it's going to be class, right? Capital C for class is our target. Again, in machine learning lingo, they call it target, where we would call it like the outcome or the response variable in more scientific language. Class tilde means our model formulas always have a tilde in the middle. The left-hand side are the responses, and everything on the right side of the tilde is our predictors, our X variables. Space dot. And the period is a shortcut, a shorthand notation for every other variable in our data except for class. So we're going to say we're going to try to use every variable to predict every numerical variable in the data set to predict class. Right? Cool. And the data that we're going to use to find these variables in is our date underscore train, right? We're using the training data, not the complete data set. We're only using the 90% of the data we set aside for training to train the model. Method means which machine learning model are we going to use? And I said random forest, and so in method, in quotes, RF, that is the name of the within caret that identifies a random forest model. If you look at in the text version of the lesson, I have a link to the documentation page for caret that has a whole list of all the different machine learning models that it has built into it on the back end. And so this is just one of them. Okay. Pre-process, I mentioned earlier today that we want to standardize our variables before we put them into the machine learning model so that they're all in the same units. Well, this pre-process will do that for you. And so this is C, which means combine to create a vector of elements. And the first one is going to be center. That means subtract the mean so that all variables have a 0 mean. The second one is going to be scale. Divide by the standard deviation so that everything is in the same scale. So basically, center and scale is the same thing as doing a Z transformation on all the variables. Okay, here's the tuning parameter that we are going to use cross-validation to identify the optimal tuning parameter that will give us the sweet spot between underfitting and overfitting in our random forest model. And I didn't mention this yet, but the tuning parameter that the random forest model uses is called mtry. And what mtry is when the random forest model is growing the decision trees, how many different candidate variables from the data set it will choose from at each time the tree makes a split. The more it will choose from, the closer fit it will get to the data, but the more potential for overfitting. And vice versa. If it looks at too few, it won't overfit, but it might miss patterns in the data, it might underfit. We want to find the sweet spot between there. And I'm going to say mtry equals 1:10. We're going to try every possible value of mtry from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to try 10 of them, do our cross-validation for all 10 of those values, and see which mtry gives us the best prediction performance. Now you can see, how did I know 1 through 10 was good? Well, because there's about 20 variables in our data set, so 10 is like about half of them. So I figured that was adequate. I mean, you can do more. There's no harm in doing higher, more possible values of mtry, but yeah, and if you don't specify these things, sometimes it will use default values, and I think it's never a good thing to assume that those default values are good. It might not give you the one that actually gives you the best prediction performance for any given data set. So that it's very important anytime you are trying out a new machine learning model to carefully read the documentation for what the tuning parameters are and what a reasonable range for them will be, so that you'll know which ones to use and not use the default values. I'm sorry? Is that, I think so, yes. I think it's like, yes, I think that's correct. It uses, I believe you're right, but I can't remember in this particular implementation what is the default. But yeah, so I mean, there's 19 variables, so 1/3 is like around 6, so that's somewhere in there. Yep. And then what is the metric we're going to use? What loss function to minimize? How are we going to look at the error of our predictions in each case? That's what the metric argument will say. And this is going to be called accuracy, capital A, accuracy, which is because we have 7 categories that we can predict. Accuracy is the overall proportion of correct answers that the random forest model gives us on the cross-validation holdout set. So we're going to try to find the mtry value that gives us the best accuracy. And TR control, we created this object a minute ago called CV_spec, which is telling it to do 5-fold cross-validation. We're going to say CV_spec, give that, telling it to do the 5-fold cross-validation. okay, this argument n tree is specific to random forest. It will only be used in random forest. How many trees are generated for each random forest model? Now this one, there's no real underfitting, overfitting issue with this. You can make this n tree as high as you want to. The only reason to not make it too high is that it will just take a really long time to run, but there's no harm in making it as high as you want. And for now, you can just take my word for it that 500 is a decent number in this case to give you good enough performance without taking a really long time to run. It should only take a few seconds or so to run this. Importance equals true means we're going to calculate, we want the model to calculate variable importance values to look at which attributes of the date are best for prediction. So we'll hit Control Enter to run this. And because it's doing 10 different mtry values each time, it's fitting the model 5 times because it's doing 5-fold cross-validation. And each of those 5 is doing 500 decision trees. So like, 10 times 5 times 500, that's quite a few. So it does take a few seconds to run this. And yep, so mine just got done. So, what was that? 20 seconds or so. And now we can spend a little while looking at whether the model had good performance in cross-validation before we go ahead and turn it loose on the test set and see if it does well. So first thing is you can call plot on the on this train object, and it will produce a plot showing the accuracy for all the different tuning parameter values we tried. So I'll hit enter on line 88. So right, the mtry, number of randomly selected predictors, and what is the cross-validation accuracy? You can see that it kind of tends to go up as mtry increases. It kind of reaches a peak here. Now, I don't know if it could be different for you if the random seed was set differently, or if you didn't set a random seed, you might get slightly different results than I did. But you should get at least get a plot that looks like this. But you can also see, well, what is the y-axis? It only goes from 89% to 90%. So actually, it looks like the accuracy of the model is very insensitive to the value of mtry, right? It doesn't hardly increase. It only goes up by 1% from 89% to 90%, depending on what mtry we pick. So it's really not that sensitive to it here. And if you get a different peak by picking a different random seed, that's an indication that it's maybe just random noise based on exactly how the cross-validation splits took place and some of the randomness in the random forest. Like if we would have to run many more iterations of cross-validation to distinguish which mtry was best, because they're so close to each other. There's really not that much difference in performance here. But here, at least in the results that I got, 6 is the optimal one for accuracy. That's one output you could get if you just type in the name of the train object in your script and just run that in your console. So hit Control Enter on line 90. It will give a bunch of default output. It says, okay, random forest, here are how many samples, how many predictors, how many classes. And then here are the accuracy values for the different values of mtry that we tried out. This is the same numbers that were in the plot I just made. Accuracy was used to select the optimal model using the largest value. The final value used for the model was mtry equals 6. You may get, your mileage may vary if you have a different random seed than I did. Another output that you often generate from a classification model is the confusion matrix. Caret has a function called confusion matrix to make one of these. I'm going to hit Control Enter to generate the confusion matrix. Cross-validated five-fold confusion matrix. Entries are percentage average cell counts across all samples. So the columns are the actual true values of what the cultivars were, and the rows are what prediction was. A perfect confusion matrix would have only positive numbers on the diagonal and zeros everywhere else, right? Like every time it was the truth was deglet, we want the prediction to also be deglet if the model is perfect, and we don't want it to predict other things. So you can see that the data are, the numbers are very high on the diagonal. That's good. The ones that are off the diagonal are a lot of times zero, but sometimes not. Like for example, 8% of the time overall, the truth was deglet and the model predicted deglet, but 1% of the time the truth was deglet and the model predicted docol and so forth. So that's what this confusion matrix is telling us. So it's taking our 90% accuracy and giving us a slightly better picture of where we got it wrong when we were wrong, right? So if we had 90% accuracy, the numbers on this diagonal should add up to 90%, and the ones off diagonal should add up to 10%. Right, because the average accuracy was 90% in our model that was selected as optimal using cross-validation. Any questions on that? Yes.
So if you use more predictor, you only use 10 for now. If you increase that number,
Well,
where you increase the accuracy?
well, let's try it out. We'll go up to 15 just for fun. And this doesn't mean that only 10 are used overall. It just means that on each branch of the decision tree, it will only consider 10 as candidates, but it selects them randomly each time. So any of the 18 variables could end up in the final decision tree. It's just that on each branch, it's how many will it select from. But let's just try it anyways and see what we get, because I'm kind of curious if it will go much above 90%. I don't think it will, because it's kind of starting to flatten off, but we'll try. Yeah, do you have a question? Yes, yeah, we're doing now. Yeah, this is kind of repetitive because we're doing 1, 2, 3, all the way out to 15. It is doing 5. It's going to take each of those 15 values of mtry, 1 through 15, and for each one, it's going to fit a random forest 5-fold cross validation with the hyperparameter mtry set to that value. So it's going to fit the model basically 15 times 5 times overall. Okay, it finished that. Now we can see how we did. Yeah, so you can see now, like, because of the different random, the randomness in the random forest, we actually got a lower mtry of 3 was now selected as optimal, and it didn't. You can see that, yeah, we're actually starting to overfit once we get above 10, and the accuracy is actually going down a little bit, which we would expect eventually it will cause overfitting. So, yeah. This is the moment of truth now, where we're going to actually see if the model, if the model does well. Because remember, we set aside 10% of the data a while ago that we never used to build the model. Now we're going to use it to validate the model. So what we're going to do is take our model that we identified as optimal, and we're going to predict the cultivar IDs of those test set values and see if it's correct. So I'm going to create an object called date predict test, predictions for the test set. I'm going to use the function predict. The first argument of predict is the model that we're going to use to make the predictions. The second argument, new data, is the the data set we're making the predictions on. So we're just going to use the measurements from the test set to give us a predicted cultivar identity and see if it matches the truth. And new data, we called that one date_test a while ago. Parentheses, if you recall. So that's what we're going to use as our new data. Hit Control Enter to execute. Now you might get different results than me because I reran the random forest again. So you'll probably get slightly different numbers than I do, but that's okay. We're going to make a confusion matrix again, but this time on the validation on the test data set. Confusion, capital M matrix. And the first argument of confusion matrix is the predictions. The second argument is the truth. And if you remember these are the predictions we just made, and date_test, $, class with a capital C, that's the column from the test data with the actual true values of what varieties they were in the test set. Control Enter. Yeah, it gives you a lot of additional input, but let's just look at the confusion matrix. You can see that it actually does quite well on the test set, right? Like this time it doesn't give percentages. I'm not sure why. In this case, it gives just integer values of the number of predictions and not percentages. You could probably change an argument to give you relative percentages, but yeah, the most of the off diagonal values are 0, which is good. You can see, like at least in my example, you know, if the truth was Berhi 4 times, it correctly predicted that, but then there was one that it said was Iraqi, even though that's wrong, and another one there. So that's how you would interpret the output of that confusion matrix. And then it gives you a bunch of statistics on the confusion matrix, like we were right 88% of the time on the test set. There's a confidence interval for the accuracy, a p-value. Is it better than randomly guessing? Yes, obviously it's a lot better than randomly guessing. You'd only be right, you know, about, hey, this is the Punxsutawney Phil thing that Brian kept trying to get me to like incorporate. Every day I've been here, he's like asked me when I'm going to talk about Groundhog Day. So I'll finally mention that that this is exactly what you'd want, you know, your confusion matrix of Punxsutawney Phil to be correct every time about predicting winter. But it doesn't necessarily mean that if you randomly guess, you're right 50% of the time, right? Because if winter lasts 6 weeks, 90% of the time, you could actually get 90% accuracy by saying winter will last 6 weeks every time. You'd never get any false negatives, but you'd have 100% false positives. So wouldn't be a very good model. But yeah, this is like that, except instead of just 2 options, we now have 7 options. So it's a little harder to randomly guess and be right if you have 7 possibilities, not just 2. And there's our confusion matrix. And then you can also, it tells you also by class how many false positives and false negatives rates you had. I won't go into all these things, but they are of interest to people that are interested in the prediction performance. Yeah, so this is a very good looking performance, but the one caveat on all this is that this is not a truly independent test set, right? Like all these photographs came from the same data set. You know, they were taken on probably the same day under the same conditions. You know, if there was anything weird about the batch of dates, like from one particular variety that all had some, you know, maybe they were like a little bigger than average for that variety or something, that little bit of randomness is baked into our machine learning model. If we went and took it live to new date pictures that were taken on different days, it would have been trained on that random noise. So this 90%, while it seems very good, is not a true test. It's still only internally valid. Because we only artificially created that validation set by splitting up our data. A true test would be to get a whole new, go out, take new pictures and see if it's right? So it may be a little over optimistic, but it's the best we can do because I don't have any access to other data sets like this. Lastly, the last thing I want to show you on random forest is, since we added importance equals true to our train function, we can actually generate a table of importance values for the 18 variables we stuck in the model, show which ones were most important for distinguishing variety. And so that was pre-calculated as it was fitting the models, and now we can extract that information in a table. The function var_imp, lowercase var, capital I, MP, gives us a variable importance. Date RF train is our model. Type equals 1 means give us overall scores. Otherwise, it would break it down by variety, and that would be a little excessive detail that we need right now. And scale equals false. If you don't do that, it will scale everything to a maximum of 100, but I want to show you, I'll explain what the actual units mean here. I'll hit Control Enter. So here we have sorted in decreasing order of importance. This is basically what the variable importance metric is here. This is one of many different metrics you could get, but the default here is if we took that variable out of the model, what percent decrease accuracy would result, right? So if we tried to predict date variety without area, we would have 43% worse accuracy. So the size of the thing is the single most important variable distinguishing between the cultivars, right? So that's what that means. Area, and then, you know, the entropy RB, which is like how wrinkly it is next important, and how compact, basically the ratio of length to width is next most, and so forth. Yeah, so if we put scale equals true, it will just, instead of giving us the percent decrease in accuracy, it'll give us the importance scaled up to a maximum of 100. So like the variable importance of area is this, and the entropy one is 73% as important as area for prediction. That's what that gives us. I will do one more thing on this demo, and then we'll take a break and do the second demo, which is much shorter. What I wanted to show you lastly, before we finish this this example with date classification, is just that random forest is only one of many machine learning models that can do classification. And the kind of nice thing about machine learning workflow, like I said, is that we can just pick and choose what model we want. Since all we care about is prediction, if we make a model that is appropriately balanced between underfit and overfit and makes good predictions, it really doesn't matter what exactly what algorithm, what model we use, because all we care about is how well we predict. So basically, there's the train function allows you to just swap out what model you're using, and other than that, the formulas and everything are exactly the same. We'll just run it again with a different model in the back end and look at the same output of confusion matrix, performance, and so forth. So let's do that. We're going to do one called support vector machine. I will not, unless people are real interested, I will not explain in detail how support vector machine works, but basically it is another algorithm that produces predictions and has tuning parameters that determine how finely it will fit the data. It's basically trying to find a multi-dimensional plane that will separate the data into categories, and then the tuning parameter says how much buffer there is on either side of that plane, basically. And if it's very narrow buffer, it will very closely fit the data and can make a very wiggly plane, but that might cause overfitting. So we try to, but if it's too wide, it won't fit the patterns in the data. We want to find the sweet spot. And here I'm going to set a random seed, and the let me see, what is it? The method here is called, there's various forms of support vector machine depending on essentially what functional form of we're going to use to split up the data, and we're going to use the linear one. There's other ones. So the method is SVM linear with a capital L. So yeah, you can see we're still using the train function with the same formula, same data, same pre-processing, but now method is SVM linear instead of method RF. And also, support vector machine does not have an mtry parameter. It has a different tuning parameter, which is called C, capital C. I think it stands for cost, but I forget. And it has different reasonable range of values. Again, you have to look up in the documentation what is a plausible range of values, or just use trial and error to find that. And basically, we're selecting values between 0.02 and 1, evenly spaced in increments of 0.02. So we're basically going to fit this thing 50 times with 5-fold cross-validation. And metric, just so you'll know, is still accuracy. So we're evaluating this one on the same basis as we did the random forest. And we're going to still use 5-fold cross-validation. CV_spec was the object we created a while back that said 5-fold cross-validation will be used. And I just am going to put this whole thing into something called date SVM train. We're training support vector machine model. I'll highlight this whole thing, which sets the random seed and then trains the model with cross-validation. Hit Control Enter to execute. And it'll take a little bit because it's doing the thing 5 times for every 50 values of the tuning parameters. So it's going to do quite a few model fits. But since it's a pretty small data set, it still doesn't take too long. All this stuff could run easily on your own laptop. We're just using SciNet, not for the high-powered computing, just because all the data examples are preloaded there. So it already got done. And now we can do the exact same things we did with the random forest model and see how well it did. So next line, I'm going to hit Control Enter to generate a plot showing the accuracy for all the tuning parameter values. You can see that, well, it looks like we actually top out at 92% accuracy with the support vector machine. So like, well, let's go with the support vector machine. It's doing a little better than random forest, and it looks like, at least with the random seed that I used, it sort of flattens off at a certain value of this seed parameter, and it doesn't once you're above about 0.6, it really doesn't matter what value you choose. You're going to get around 90%, 92% correct. And then, yes, I'll just execute the next 2 lines to generate predictions on the test set and then make a confusion matrix just as we did last time. Control Enter, that generates the predictions. Control Enter, I've got a confusion matrix. And yes, you can see that usually your accuracy on the test set is a little bit less than the cross-validated accuracy on the training set, right? Because the model was fit on the training set. So the accuracy should go down a bit when you get to the test set. It was 92 on the training set, but it's still 89% accurate on the test set. Once again, that's really good, but it's we don't truly know if the training and test set are independent. Oh yeah, and here's the no information rate. That's like if you were randomly guessing based on the proportions that were in the data, you would be right 23% of the time, but the model's right 89.5% of the time. Yeah, so that's it for the first demo. Let's take a break until 11:30. If anyone needs help with the code and stuff in the interim, we'll help you. Otherwise, we'll take a break till 11:30, and then I just have one last quick example for a regression task that we can do, and then call it a morning. So yeah, let's take a break till 11:30. Did you get the code figured out? Okay. Yeah, it could be, yeah, you know.
My graph
the
is
random
different.
seed.
Yeah.
But at least
It shows my.
you got a graph, you know, you got about the same result.
Right.
Yeah, so,
Quite a few examples where it seems like everybody was saying something different.
Yeah.
They're doing the same thing, but not the same. Yeah.
I kind of admit that they have.
I see.
Same code, right? It shouldn't
So
be.
I might have like accidentally skipped one of the set C lines when I was doing the training test split. I think I might have forgot to run that, so. I believe I did, yeah. I didn't do the set C one right before the training test split. Yeah, that's why you do usually not just do one split like that. You would do it multiple times because the results are a little bit sensitive to exactly what is in the split, you know, yeah.
So do you have notes somewhere like how to upload, like if there's something in Excel sheet, and I want to create some GB plot or something like that, or a heat map? We have notes somewhere that how you take the data. Usually
Just like
it's a
importing the
CSV.
data into-
So.
Yeah,
And what code you will use so that you can use your example split sheet and like copy it, but I don't know.
I can help you, if you need help just importing data into R, I can help you with that. And some of my lessons have like examples of importing data, but,
Yeah, maybe
Yeah.
share those.
that you can.
I don't have any data now, but
Okay.
I'm seeing for the people.
Okay, yeah, look, crooked, how you doing? Good. Good. Maybe we'll change
Not,
that.
I don't want the assembly.
It's not straight. Whatever.
Has them.
Nice. Thanks for staying on top of the chat there. Seems like you know this one. Yeah, I've done this one like I think 3 or 4 times now, so, yeah.
It's long, so many for countries. The other one got 255. That's very much.
Look at the, let's see. What about these, the halfway down too? How many countries are in that geometric chart?
So, yeah, that
Yeah.
is, that is the hyperparameter. We are using unigrid, right?
Mhm.
That is the hyperparameter, right?
It is.
So for
So
the,
it's selecting it internally. It's not actually.
for random numbers, those hyperparameter will be lactose.
Yeah. Mhm. Yeah.
But here, they it can take all the variables, but it's a different.
Yeah, I don't remember exactly what this parameter means. You can look at the documentation. on the manual, there's like the buttons on it. Let's see. Oh, looks like that's the. See the. You remember what C means?
I can't remember what it stands for, but basically like I think it's cost, but it's like a support vector. Basically, when you create a hyperplane that separates the categories, support vector are the vectors extending from that hyperplane to the points that are closest to the separation line. So only the ones that are closest to it are actually used to generate the hyperplane. The C thing will like make a buffer around the hyperplane and like only and kind of like not use ones that are too close to it, I think. And I think that's how it works. But
Okay.
yes, I've seen there's like
Or one is the graph, that is.
Yes. there's like some I should have put in some like images of how the support vector machine works. Let me see if I can find one that's that illustrates it. I mean, Wikipedia usually has
Large value of C will choose a smaller margin hyperplane if the hyperplane does a better job of getting a multi-training classified correctly.
yeah, so here's like if a support vector machine had two categories you're trying to predict between, you can see there's like this line, everything on one side of the line belongs to one category and everything on the other belongs to the other category. So like the C will this one doesn't, yeah, this is not a good example because there's the only reason that C matters is when you have ones that are wrong. Let me see if I can find a better picture here. Let me see. Um, I see. Okay, yeah. So basically, the if you have a low value of C, it will make the plane that separates the categories smoother and have less wigglies on it, even if it gets some of them wrong. A high value of C will try to make a surface that will exactly separate all of them, but that leads to overfitting, right? Because but so if you have a lower value of C, it allows a few of the things to be wrong as long as but it has like less parameters basically. So it's just like how uh, smooth versus how wiggly the regression is that's separating them. I'm trying to find like a good picture of it. Yeah, but I didn't make one for support vector machine in particular. Trying to find a try to find one. Oh yeah, here's a decent picture. So yeah, here's like if C was low, we have a larger buffer around it and there's more incorrect classifications. C is high, it's a narrower buffer, it's a tighter fit, but it can be overfit, if that makes sense. But like, it's harder to interpret like exactly what the number means. With the M try, it makes sense. I'm not sure exactly what the number represents. It doesn't really have a meaning. So that's why you have to try out different ones for your data set. Yep. I don't actually know what the absolute value of it represents. I don't think it has a good interpretation. But thanks for asking though, because yeah, I don't really know myself. And start back up. Shouldn't take too long to finish up the last demo. So we'll take our time. Okay. Okay, so it's 11:30. We have one more demo, and then our exciting week of stats training will sadly draw to a close. Let me see if there's any slides that I can show for the last bit of this. Yeah, and this last example that we're going to do, I told you that you can use machine learning models for classification, predicting a discrete variable. Well, you can also use them for continuous variables, such as yield that we might want to predict. We could also just continue to use random forest. Random forest can work just as well with continuous outcomes, but I'm just going to show you a different type of machine learning model here just to give you a bit of idea of what's out there. So we're going to use some actual ARS data for this example, although I've added a bit of random noise and taken away identifying things on it. In the world of sugarcane, sugar yield is king, and that's measured in tons of sugar per hectare. TSH is where the money's at, so that's what we're trying to predict. And it's a regression, obviously, because it's a continuous variable. What this researcher wanted to ask was if you could, let's say in a some sort of breeding operation, you could save time if before you actually went and extracted the sugar to measure the yield, you could predict it by just taking pictures of the canes in the field with a hyperspectral camera and then use different wavelengths of light coming off of that to predict yield. That would be nice. So they that's just one of the things they were trying to do with this. But they flew drones over a bunch of fields and took pictures with a special camera that gives you reflectance at many different wavelengths, like at every different shade of green coming off the thing, like how intense was that light coming off of it. And then there are different, you can just sort of like plug those wavelength values into a formula to get different vegetation index values that people have seen in the literature are meaningful. So we basically just have a bunch of, for every image, we have a bunch of numbers. Some of them are wavelengths and some are these different metrics that are just like calculated off of the wavelengths. And here in this example, I've got all those numbers. I've got the outcome value, which was later they did actually harvest these plots and measure the yield. So we actually know what the yield is. Now it's like, well, could we have predicted it beforehand from the pictures? And there were different treatments and different genotypes, but I've excluded that information just for the purpose of this demo. Let's just say we don't know that, and we're just trying to predict the yield just from what it looks like. That's the only information but we do have the rep. So because I did want to illustrate how we could do cross-validation in a study that has blocks that has reps, we're gonna do the cross-validation by rep. So I've kept that information in the data. And we are going to use a type of model called lasso regression, which is kind of a very simple machine learning model to try to predict yield. And lasso regression is basically just a multiple regression using a bunch of X variables to try to predict a Y variable, but the only tweak it has on just a standard regression is that it includes a regularization parameter, right? Because machine learning models have regularization parameters to balance between underfitting and overfitting. And remember, each one has its own name. Like we've seen, mtry was one for random forest, C was for support vector machine. This one's called lambda. And the higher, basically, if you set lambda to 0, it's just a multiple regression, no different than any other regression we might do. But the higher lambda gets, the more coefficient values get shrunk towards 0, and some of them, if lambda's high enough, just become 0 entirely and drop out of the model. And as a result, obviously, because we have, if that would happen, if we do shrink the coefficients and drop them out, we get a simpler model that does not fit our training data as closely as a standard linear regression would do. But because it's not quite as close of a fit to our training data, it might make better predictions on new data, right? That is what our hope is. But obviously, if we make it too high, it's going to miss patterns that exist. So we have to find the lambda that balances those two things, just like we did for any other tuning parameter. Yeah, so that's really the background I have. So now we're just going to spend the rest of the time exploring the data, doing any pre-processing we might want to do, and then fit the model and see how it does. So here we are. I'm now down back to RStudio server. I'm on line 131. If you're on the demo server on Cynet, you can just run line 131 to import from the data folder. If you're on your own machine, I put this on a URL that you can import from. So I'm going to run line 131. People running their own R would run line 134 instead. I'll skip that line. So yeah, sugarcane is a data frame. It only has a little over 100 observations. Those are the different plots that they took pictures of. And it's got 20 variables. One is the yield variable, the tons of sugar. One is what rep it comes from. And the rest are different reflectance values at different wavelengths. So I'm going to, this next line 136 pulls out the names of the columns other than the TSH yield column and the rep column. It pulls out those names, and then we're going to make plots of all the predictor variables. I'll hit Control Enter to execute that. The next couple lines produce a bunch of scatter plots. I won't explain exactly the code that goes into creating those scatter plots, but we'll run this line to generate the scatter plots. And then this next line with wrap plots will display all the scatter plots in a matrix on our plot tab. And it also includes a little smoothing line on each one to give us an idea if there's a relationship. So every one of these scatter plots has the one of the different reflectance values, like these are the different wavelengths of light, nanometers, and then how intense was the light coming off the sugarcane at that wavelength, and then TSH is the yield plotted on the y-axis, and then there's different vegetation indexes calculated off those reflectance values. So it's like, okay, a lot of these don't seem to have a lot of relationship with yield. Maybe a few of them, if you squint, it's like, okay, maybe if it's NDVI RE800 goes up, yield might go up a bit, but there's a lot of noise, a lot of random variation too. Yeah, so maybe we can predict yield off of these things, and maybe not. I wouldn't get super optimistic if I saw these scatter plots, right? But we can at least try. Now we will make a heat map just like we did last time to see if any of these values are correlated with each other. I'm going to do that. So I'm going to use the core function to create a correlation matrix of the predictor variables. Oops. And I called which columns we're going to make the correlation matrix of. I made the vector called sugarcane underscore predictor underscore variables. Start typing that and then hit tab to finish. Whoops. And it's going to make the correlation matrix of just those columns. Hit Control Enter to execute that line. And then hit Control Enter to make the heat map. As you can see, there's really, even though we have, 18 predictors, we don't really have 18 predictors worth of independent information because a lot of them are highly correlated with one another, which, it makes sense because they're very finely spaced. The vegetation indexes are using some of the same information. It's like we're using, the 680 through 800 nanometers vegetation index, and here's like the 680 through 710 vegetation index. Those are like probably very similar since they're using the same information to compute. So many of the things are very highly correlated with one another, but they were just using a kitchen sink approach and trying any index that they thought might be useful. So in many cases, I would go and throw out correlated predictors, but I'm not going to do it in this case because I wanted to just demonstrate how lasso regression can internally shrink the coefficients of correlated predictors towards zero. And then, so we don't necessarily, you could also do a two-step approach and get rid of some predictors first and then fit. I encourage you to play with this stuff in the example data and try that if you want, but I'm not going to do it here. This plot here. Yeah, so what you would do to export this plot, there are like the point and click way to do it. You can see it says export here. You could click on that and save as. Yep, so we could like set the dimensions of it and like where it's going to be saved to. This one would save it to a folder on Scinet, which you would have to then, but if you ran this on your own machine, you could save it to your local hard drive. Otherwise, you could also, if you want more finer control of like the dimensions and the resolution and stuff, you would use the function ggsave to save the plot to, yeah, if you want, I can show you, but yeah, you would do like ggsave and we'll save it to, here. Yeah. And just save the shared. This is how I would do that. Correlation matrix dot JPEG, and you could say, okay, we want it to be, 5 inches by height by width, 5 inches, and DPI 300 for a high resolution image. If I did that, now there's a correlation matrix.jpg in here that I could then save to my local hard drive if I wanted to. Yep, so there's the plot. I mean, not perfect, but you'd have to tweak the appearance of it a bit. Okay, so I mentioned before that if you have blocking in your data, you want to keep the blocks separate in your cross-validation folds and not use data points from the same rep across in between your cross-validation folds. And I'm kind of skipping the step here of doing a separate training testing and then I'm just going to do cross-validation on the full data set. It's a very small data set, so we can't really afford to set too much aside for final validation. And because this is more about, inference as well as prediction too. So that's another reason there. So what I need to do is make a custom function to, instead of before with the date fruit, all those data points were independent. So we could just let it randomly decide which data point would go into each of the cross-validation folds. Here we have to manually or sort of explicitly say, okay, we're going to split the data up for cross-validation. And there are 6 reps in the data. They're numbered 1 through 6. So I decided 6-fold cross-validation is fine. We're going to fit the model, let's say, to reps 1 through 5, use it to predict the data from rep 6. Then we're going to fit the model to reps 1, 2, 3, 4, and 6, and use it to predict rep 5 and so forth until we've predicted data from all the reps. So we want CV_folds. What we're going to do now is use the map function, which will create a list for each rep. It will be the rows of the data from that rep. So I'll show you what that looks like in a second. So we want for each value of X from 1 through 6, what are the rows of the sugarcane data that are from that rep? That's what we're going to get. Sugarcane, which parentheses sugarcane $ rep is a capital R is equal to X. Hit Control Enter. And now your CV folds, you can see it's a list of 6. So like the first one is the 24 rows of the data from rep 1. These are the 24 rows of the data that belong to rep 2. These are the ones that belong to rep 3 and so forth. Now we'll do another, remember how we had to last time tell it to do 5-fold cross-validation. Now we're going to tell train to do 6-fold cross-validation and specify that we don't want it to just use any old folds being how the data are split. We want to use those specific folds that we have created based on the reps. So CV spec sugarcane, we're going to use the train control function as we did last time. That means here are the arguments for how we're going to build the model. We have a question in the chat. Which one would you recommend for quantitative trait predictions? Lasso, Bayes A, and Bayes B. Yeah, I think, it's often good to try out different ones and see how they perform. I think Lasso is kind of one of the simplest ones, so it's the easiest to interpret, which is nice. Yeah, I think I don't really have a lot. I mean, I've heard of Bayes A and Bayes B, but I don't know exactly that much about how they work. So I would have to, I don't have a good answer for you right now of which one like performed better. I don't know, Grant, do you use those ones?
Yeah, I'll put a link to a review article that talks about it.
Awesome. Thank you, Grant. Hopefully that will help answer your questions. But I mean, I have seen them all used in different contexts, but I don't have a lot of experience myself with it. Yeah, so we're gonna do cross validation. Number equals 6 because we have 6 cross validation folds, and index out means which rows will belong to which fold, and that's going to be our CV underscore folds object we just created. So it's our, for each fold, which rows of the data are going to be in that split. Method equals CV, number equals 6, and index out equals CV folds, and we're going to pass all that to the train control function. Control Enter to execute. Okay. Now here, again, excuse me, we're going to use the train function to set up our all the arguments that we need for training the model, and then it'll actually go ahead and do it for us with cross validation. For train, instead of passing a formula and a data argument, you can pass it a matrix of predictors for X and a single column of outcomes for Y using the X and Y argument. So that's what we're going to do here. This code basically takes the predictor columns out of sugarcane, and instead of being a tidyverse data frame, it just turns it into a regular R data frame. Y variable is the column of sugarcane that has the yield, the sugar yield information in it. So that's going to be sugarcane $ means pull out a column, TSH in capitals. So that is the yield that we're trying to predict. Okay. Method is glmnet. That is the name of the R package that implements lasso regression that we're going to use. Preprocess equals center and scale, just like we did last time. We're standardizing because all these things are in different units, and we're standardizing them to all have a mean of 0 and a standard deviation of 1. Tune grid. We want to use the function expand.grid, which will give us all combinations of the, so there's, well, I guess we don't really need expand grid because we only are using one value. There's 2 parameters to well, this is an elastic net regression, which lasso is a subset of. Alpha equals 1 means we're going to do lasso regression. I won't go into exactly what the difference between lasso and ridge regression is, but they are different types of regularization that is done. But alpha equals 1 means do lasso regression. And then if you remember, lambda is the name of the regularization parameter. Lambda equals 0 would mean don't do any shrinking, just give us a regular regression. So we're going to start with a lambda that's very close to 0 and go up. I mean, lambda can go up to infinity essentially, but we're going to, based on my trial and error, I found that these are good values for lambda in this case. You would have to, if you're using your own data set, you might have to try different ones. Metric, we don't have accuracy anymore because we're not predicting a specific category. We just want to get as close to the correct yield number as possible. So we're going to do RMSE, root mean squared error. That's just like a regular linear regression, minimize the sum of the squared error. That's just exactly what a regression is doing. So this is just regression with one extra tweak of picking the best lambda to maybe shrink some of the coefficients towards 0. Train control, we're going to use the CV underscore spec underscore sugarcane that we created a few minutes ago that tells us what the folds are. Okay, so I'm gonna highlight this, which I'm gonna set the random seed and then do the 6-fold cross validation to fit. This should only take a second because it's only fitting a very simple model 6 times. Whoops, I'll highlight this and hit Control Enter. So it runs very quickly. Now, yeah, that was it. And now we're just going to evaluate our model and see if it did good job predicting and what the predictions were. First, we'll call plot on it, just like we did with the random forest model. This will again show us our performance. This time it's the root mean squared error for every value of lambda that we tried out. And here, right, low, last time we wanted a high number because we wanted more accuracy. This time we want a low number, low error. So we see that the root mean squared error is low at this particular value of lambda. Now, you can see the root mean squared error actually is not too variable based off of that. The lowest we can get is to be within 5 tons per 5.4 tons per hectare. The worst is being wrong by root mean squared error being 5.7 tons per hectare. Is that very good? You know, probably not. I can't remember what units. Let me look at the sugarcane data. You can see that TSH is like, if you look at somewhere like 25 tons per hectare, 24, 15. So it's like our error is 5. That's horrible because like the thing is, you know, they only vary by 4 or 5 tons per hectare at most anyway. So is this good enough to take it live and actually predict sugarcane yield with? I would say not really, right? This is just to illustrate, you know, this stuff isn't magic. And if there's no signal in the data, you're not going to get good performance and it's not useful. Yes, but lastly, so yeah, this plot is already telling us that, but we're just going to make a couple other diagnostic outputs to look at it a little bit more. If you extract the object called best tune from the fitted model object, it will tell us what the optimal value of the tuning parameter lambda was that minimized our error. So I'll hit Control Enter to execute that. You can see that the lambda 0.01 was found to be optimal, which is just what we see in this plot. Again, if you use a different random seed, as I did, you may get different results. Yeah, because with these very small data sets, things are very sensitive to the randomness. For folks that are leaving, thanks, Yavuz, for participating. Let's see. Oh yes, I didn't put this in the worksheet, but if you just type the name of the fitted model object in your console and hit enter, it will give you a bunch of output. ESH underscore lasso underscore fit is what I called it, tons of sugar per hectare. You can see here are the, it gives you some info about the cross-validation process that was used. And then here for the different lambdas, what was the average error, and what was, it also gives you an R squared and a mean absolute error, which again, we could have tried to minimize mean absolute error instead of the square root of the squared error. It would probably give a very similar, not always, but it usually gives similar. So you can see that the R squared is at best 0.3, you know, is that good enough? It depends on your needs, but I would say for most use cases, probably not. And then, yeah, as lambda increases, we actually start to underfit because we're making too many coefficients go to 0. It starts to go down. If we would have used even higher numbers, eventually the R squared would go to 0 because if you set lambda high enough, all the parameters eventually go to 0. So it would start to go down. So we can see that, you know, that's where it starts to drop. Yeah, and I just like to use this one as an example because a lot of like machine learning classes use like cherry picked data sets that have really good performance, and then it gives you an overly optimistic idea of what these things can do. But it's like, well, you know, garbage in, garbage out. Sometimes the the scientist was interested in seeing if this signal existed and could be used. We found it's not, and that's okay because that we learned something from that, but it's not a good predictive model. So basically, this code here is kind of complicated, but it is used to extract. There may be some easier way to do this, but I couldn't figure it out. To extract the coefficients associated with the optimal value of lambda so that we can actually look at what the parameters of the model are. So we're saying the minimum from the final model, the minimum lambda, basically every blank I've here, replace it with the word lambda. The minimum lambda for those cases where the minimum lambda that is at least as greater than or equal to the lambda that was identified as best in our cross-validation. Which lambda is it? And then figure out which row that is in the final model object. And then use the coef, use the coef function to pull out that column of coefficients from the matrix. That's basically what this is doing. You don't really have to get into it too much. But then what I wanted to do is just pull out the coefficients that Lasso identified. And then I'm just going to use the LM function here to fit just a regular multiple regression, not using any machine learning stuff, just using the coefficients we get from a regular regression with no shrinkage, no regularization. And then I'm going to just put a table of them next to each other so that you can see how using Lasso instead of just a regular regression changed what the coefficients are. So first I'll run this to do that. You don't necessarily have to run this on your own if you don't want. You can just take a look at what I'm doing. This is more for illustration purposes. Then in line 188, this just runs a multiple regression without any regularization and pulls out the slope parameters. And then I'm going to round it to 3 decimal places. Show in one column the best coefs, which is the coefficients from the best model we identified with cross-validation. And then the unshrunk coefficient is the coefficients of the regular normal linear regression without shrinkage. Hit Control Enter. And here's what we see. Yeah, the intercept is the same for both because intercept is not regularized at all with lasso regression. It gives you the same intercept as a normal regression would do. It doesn't try to do any, it wouldn't make sense to shrink the intercept towards 0. So yeah, you can see the lasso coefficient is always smaller, less than or equal to the one you'd get from multiple regression, or the absolute value of it is smaller because it's pulling them towards 0. And I think, yeah, one of them goes to exactly 0 and drops out of the model entirely. But, you know, some are shrunk more than others. Some are shrunk very far towards 0 and some only a tiny bit. Actually, this one has a larger absolute value. So I guess it doesn't always have to be smaller. Yeah, that makes sense. Yeah, so anyway, that's just an illustration that we're actually shrinking these numbers towards 0, not fitting the data as closely, but possibly getting better predictions on new data. But again, better is relative. Our performance wasn't that good, so really it's in an absolute sense not a great model. I wouldn't go and bring it to sugarcane growers and like hype it up as the next big thing in yield prediction, right? So yeah, that's all I've got in terms of demos. Let me just, let's see. I have a couple of recommendations of especially the book Introduction to Statistical Learning. Grant, I don't know if you've ever gone through that one, but it's sort of like a great one to take to a desert island if you really want to learn like the basics of how machine learning works. This is the book. The people that wrote it, like invented lasso regression and also pioneered a lot of other techniques. So they're very qualified to talk about it. And there's different versions of it. One uses R implementations, and I think there's like a Python version of it too. So you can pick whichever one you like best. And there's a couple other tutorials I've linked to there that you can use. And as I mentioned before, if you look at the text version of this lesson, there's some like homework problems you can do if you're not tired of doing this stuff yet and want to try those. And the answers are also in there. Yes, and just one last thing before we open for Q&A. If you go down to the very bottom of this week's page, there's a link to a feedback survey. It would be very helpful for me in improving future lessons if you would fill that out. And if you have an idea, of a future of another class you want me to teach, or like materials you want me to develop, throw that in the comment box and I'll put that on my to-do list. Yeah, so that was that's all I've got for today. I'm just gonna go ahead and stop sharing and stop recording, but I'll stick around for a bit here to take any questions that people have. Thank you for participating. Oh, and I should have said